So my name is Jake Helton. I'm a fourth-year graduate student at the University of Arizona. Today I'll be talking to you about high-redshift galaxy overdensities that we found with JWST. And so let's begin with this map of the local observable universe. This is made by researchers at Johns Hopkins University using data from the Sloan Digital Sky Survey. And you can see there's lots of structure here. You know, there's these extended linear filamentary structures. There's these empty regions of space called voids. And there's these nodes, these very dense regions of space, the so-called cosmic web. Galaxy clusters inhabit the nodes of the cosmic web. They contain tens, hundreds of thousands of galaxies in a very small volume. And these are the most extreme entities allowed by our understanding of cosmology and hierarchical structure formation. So what does our understanding of cosmology and hierarchical structure formation predict? This is a simulation from the TNG cluster project, showing the evolution of a massive galaxy cluster from redshift 20 down to redshift 0. Observationally speaking, we've known about galaxy clusters for about as long as we've known about galaxies. So roughly 100 years ago, Edwin Hubble found the first extragalactic source in GC 6822. A few years later, in the 1930s, he published his famous velocity-distance relation, or so-called Hubble law. And actually, in this paper, he identified 8 galaxy clusters, including Virgo and Coma. Many decades later, in the 1980s, Alan Dressler published the morphology density relation and found that these galaxy clusters had a profound impact on the properties of their constituent galaxies. And since then, we know that star formation rate, emission line strength, rest frame color are all dependent on the local density or the local galaxy overdensity value for the individual galaxies. But as of right now, this is something that is only understood up until redshift 2 observationally. You know, we have the theory, but observationally only understood up until redshift 2. And so why is this only understood up until redshift 2? So first and foremost, galaxy clusters and protoclusters are difficult to observe beyond redshift 1.5. The main reason that systematically searching for these things requires deep X-ray or sub-millimeter observations to try and detect the ICM. We're not, unfortunately, sensitive enough to do this beyond redshift 2 or so. I think there's a couple of cases, but statistically speaking, not very easy to do beyond redshift 2. Systematically searching for protoclusters relies on different things. And just so we're on the same page, when I say protocluster, I'm referring to this extended overdensity of galaxies beyond redshift 2 that would eventually evolve into a galaxy cluster by redshift 0. So when you look for these things, you typically look for these overdensities of galaxies, typically special ones, red galaxies, submillimeter galaxies, Lyman breaks, Lyman alpha emitters. And you typically, or people have typically searched for these around these rare and luminous sources, such as quasars or submillimeter galaxies, since these things are expected to live in the most overdense regions of space. But searching for protoclusters and searching at these redshifts has been limited by the lack of large representative samples, spectroscopic samples, of redshifts beyond redshift 5. This was all prior to JWST, of course, and now JWST is changing things. It is now possible, or more easily possible, to get large representative samples of star-forming galaxies with spectroscopic redshifts beyond redshift 5. And there's been a large number of overdensities, galaxy overdensities, or protocluster candidates found already with JWST with the data we already have. And so the ones that are in the upper part of the slide here, these are ones that are identified with NIRCam, specifically the wide field slitless spectroscopy mode of NIRCam. There's a few dozen here that have been found beyond redshift 5 to date. I think I included everything. There's inevitably something probably not up here. At the bottom of the slide, this is ones identified with NIRSpec. The first 2 with multi-object spectrograph, the bottom 3 integral field spectroscopy around these very special sources. Today, I'm primarily talking about how I systematically search for galaxy overdensities or protocluster candidates with JWST in the Goods North and Goods South field at high redshift, beyond redshift 5. And so, as I mentioned, it's very important to have this large representative sample of star-forming galaxies. And to do this, I use JADES, GEMS, and FRESCO surveys from JWST, 80 square arc minutes, and built this largest at the time sample of spectroscopic redshifts beyond redshift 5. I think Anna Christina Eilers that they showed earlier for Eiger, it beats me by a little bit, 830, but at the time, the largest existing spectroscopic redshift sample. 775 galaxies between redshift 4.9 and 8.9, The redshift histogram on the left shows the Goods North ones, nearly 400 of them in red, and nearly 400 in Goods South as well. There's 615 H alpha emitters, 160 O3 5008 emitters, and the way we found these spectroscopic redshifts is with the imaging. We have good photometric redshifts. We identified a single emission line in most cases at 3 sigma, either H alpha or O3. And you can already start to see these overdensities appear just in the redshift histogram. Many of these peaks that appear here are ones that I will later talk about and find. So there's one here at redshift 5.2 in Goods North in red, one at 5.4 in blue in Goods South, and then even all the way out here, 8.2 in Goods South, the blue. This is also apparent over here on the right where I showed the slitless spectroscopy we have for these 775 sources. So H alpha is going to be down here from redshift 4.9 to 6.6, and for almost all these, it's a single line detection of H alpha. Above, you get the O3 emitters from 6.8 to 8.9, and for some of these, it's only one line, but for a lot of these, you can see the doublet. We get 4960, we get H beta in some cases. And as you could see over here in the redshift histogram, you can also see these vertical stripes corresponding to some of the overdensities that we later find. The one at 5.2 in Goods North I pointed out over here, the one at 5.4 in Goods South I'll talk about later and found last year. And so here are those sample of overdensities that I ended up finding. And so to do this, I measured galaxy overdensity values for each individual galaxy. I then used a grouping algorithm, a friend-to-friend algorithm, to identify potential structural groupings, and then used theoretically motivated selection criteria on the minimum number of constituent galaxies, as well as the average galaxy overdensity value within the overdensity itself, to identify the sample of 17 overdensities in Goods North and Goods South. The first 5, the top 5 up there, these have been ones that have been written about before. They're well known in the literature, at least for a couple of years, some of them for a decade or more. The bottom 12, these are all newly discovered overdensities with JWST. Many of these just of regular, typical star-forming galaxies. And maybe the most interesting are the 2 down at the bottom, which are the 2 highest redshift spectroscopically confirmed overdensities to date at redshift 7.954 and 8.220. Let's look at the 3D distribution of these overdensities. And so I have these movies that I made. This is the one at redshift 5.2 in Goods North. It comprises 3 distinct overdensities. The largest one with over 100 members over here on the left right now. This is surrounding the well-known dusty star-forming galaxy HDF 850.1. The one on the, well, now it's on the left, but the higher redshift one is around the well-known dusty star-forming galaxy GN10. Very weird, elongated filamentary structure. Here's one at redshift 5.4 in Goods South that I found last year. The overdensity itself has nearly 40 members in this very, very contained volume compared to only 30 members in this much larger volume along the Lana site. This is a 10 times overdensity compared to the background average or a random volume. And then this one, the highest redshift one that I identified at redshift 8.22. It has 6 members compared to only 2 in this much larger volume that you probe. This is a 12 times overdensity. I measure the halo masses for these. I measure stellar masses for individual galaxies, use an empirical relation and try and measure the halo masses for everything. That's what's shown here in blue and in red. I compare with theoretical predictions for the evolution of a massive galaxy cluster in brown by redshift 0. And I also compare with universe machine light cones, and I derive theoretical galaxy overdensities using the same observational selection that I do to try and see if I'm recovering the same thing that the theory would recover. And based on the total number, the redshifts, the halo masses, stellar masses, star formation rates, what I am finding is very, very similar to what the universe machine predicts. And based on the selection, as well as the number densities that I find for these overdensities, I suspect that the majority of these, most of these, will evolve into a massive galaxy cluster with halo masses larger than 10 to the 14 by redshift 0. And the last figure I want to share is on the y-axis, these galaxy overdensity values that I measured, and on the x-axis, the rest UV properties of these galaxies. And so on the y-axis, as you go up, this is increasing density. There's more galaxy neighbors up top. If you come down here, there's fewer galaxy neighbors here. As you move right in the left panel, these are the brightest objects and the reddest objects. And the gray points are the final spectroscopic sample. And so you can see there's this trend as you move to the right in the figures that you're moving upward. The locus of the gray points is moving upward. And this is most readily seen in the green points, which are the median values. And so what this is telling you is that as you go to the reddest and brightest objects, these are the ones that are preferentially found in overdense environments. You can measure linear regression. This is a more than 6 sigma correlation, more than 3 sigma correlation. And we interpret this as evidence for accelerated evolution or more evolved systems within overdense environments. And just to quickly summarize the stuff I just said about this paper, we built at the time the largest spectroscopic sample of galaxies, 775 star-forming galaxies between redshift 4.9 and 8.9. We found 17 galaxy overdensities within this large sample, 7 of them in good north, 10 of them in good south, many of them never known before. Roughly a third of our spectroscopic sample ended up as part of these overdensities, and so a large fraction of the galaxies that you might find could be part of these overdense structures. And more than 83%, if you look at the galaxy overdensity value, is more dense than the background average, as Peter Baruzzi was kind of talking about or alluding to half an hour ago. The final sample includes the 2 highest redshift spectroscopically confirmed overdensities to date at redshift 7.954 and 8.220. And the UV brightest and reddest objects appeared in the most overdense environments, which we interpret as accelerated evolution. And finally, I wanted to summarize the current status of what the environmental impact is with JWST beyond redshift 5. So we heard, a wonderful talk earlier from Anna Christina Eilers about quasars preferentially being found, not always, but preferentially being found within these overdense environments. Dusty star-forming galaxies as well. What I just showed, the typical star-forming galaxies as well. Evolved systems such as the UV red or UV bright, the weak emission line galaxies, the mini-quenched, these also seem to be associated with overdensities. LAEs, we just heard a couple talks about that, are also found. And maybe even these massive neutral gas reservoirs. And so I want to thank you for your time. I want to thank the organizers for having me. And, there's a lot more I'd like to talk about, future plans, photometric clustering. Feel free to ask me. I have some slides I can share. So thank you.
Next time. Thank you. Thank you so much also for being on time. So if you have questions, so one is from Rafaela.
So thank you very much. Beautiful results. I'm curious to know if you have tried to correlate these overdensities with the presence of these faint AGN. So are these sitting preferentially close to the overdensity? What is your understanding of that?
Yeah, thank you for the question. Ongoing work, I don't think I have a good figure to show for this, is looking at the correlation functions for galaxies within the spectroscopic sample as well as the AGN, like the type 1 AGN galaxy correlation. Just looking at galaxy overdensity values, the LRDs or the type 1s that we find in Fresco or we now have Congress data, these are preferentially in the overdense environments. Many of which, more than half, are within these very large-scale overdensities. So, for example, the redshift 5.2 Goods North one, very extended. It has the dusty star-forming galaxy HDF 850. It has 5 type 1s from the Fresco data associated with it, which is more than half of the total type 1s for all of Fresco. So these type 1s and AGN in general, we are finding that they are associated with these overdense regions.
Yeah, question from the back.
Yeah, amazing talk. I had a question about your last slide.
Yeah.
So the last slide.
Yeah.
And again. So the plot.
This
there
one.
we go. Yeah. So this is a really interesting plot. So you can see the clear correlation here. But I guess what we really want to know is, are things redder at fixed MUV
Yes.
or fixed M star? And so more clearly determine the environmental impact here, rather than just this correlation may just be driven by the overabundance in overdense environments.
I agree. Thank you for asking that. Specifically this right panel here, where there's this underlying correlation between MUV and beta UV. I did not do this for this paper. In future work, I would like to try and tease out what this is definitely the underlying thing, and then whether this persists after correcting for that is still up for debate. I don't have an answer for that. I will use that as a segue to show a in preparation thing, which is looking at line ratios. And so if it was just an MUV thing, then maybe once you correct for MUV, the beta UV, the correlation goes away. But we're also seeing evidence for increased O3 over H beta or increased Balmer decrement as you go to these larger, these more overdense regions, which you could also then need to correct for the MUV, which is not done here. But there is this evidence that there's more metals and or more dust in the more overdense regions, maybe corroborating the beta UV correlation.
Alice. Okay, can you use that mic? Thank you.
Thanks for such a nice talk. So I guess on the same topic, I mean, so I guess my question is sort of like, what are the predictions for accelerated evolution beyond Redshift 5? Because the whole age of the universe is so young at that point. We looked in overdensities at Redshifts 2 to 3, where maybe there was some evidence. So I guess that's one part of it. And related to that, you know, MUV, we've talked a lot about bursty star formation histories.
Yeah.
MUV, and then beta also has multiple interpretations in terms of either the dust or the age of the stellar population. So I'm not sure that either MUV or beta is a marker of a more evolved galaxy as opposed to a young dusty galaxy.
Yes, good point. The conclusion of accelerated evolution is primarily related to the MUV, and that these are more massive. You can look at the stellar pops as well, more massive, brighter things.
Right, but haven't we had a big discussion about MUV and how well or not well it's related to mass?
That's correct.
Do you have the masses?
Most of these sources are at Redshift 5 to 6. I would argue that I think we know maybe not the stellar masses to the best degree, but for a statistical sample where you are self-consistently modeling everything, I think the correlation persists. And so one can...
You just measured the stellar, you guys estimated the stellar masses?
Yeah, this, I'm not showing it, but the figure from earlier, this persists for stellar mass. You can also see correlations in star formation rate. You also see differences in the star formation histories. The ones that are in the most overdense regions have a turnover in the more recent star formation history, more extended to 50 to 100 million years rather than just limited to 10 or 30 million years for the underdense regions. The stellar pops were not really explored in this paper because of this hard to do with the UV properties conversion to stellar pops, but that's something that I want to more carefully do in future work.
A very short final question and possibly answer.
Yeah, I'll be fast. So you said 30% of the objects lie in a large-scale structure, which I presume is a protocluster in your system. Your masses are quite high. So Eilers finds the O3 emitter clustering is basically consistent with halo masses of 10 to the 10.5. Your masses seem high, and that's 30%. So I was just wondering, have you thought about whether those are commensurate with each other?
I have not directly compared, but just to give you a sense of the stellar mass, star-forming main sequences for the redshifts, and so this gives you a sense of the stellar mass range.
I'm asking about halo, dark matter halo masses. I hate stellar masses.
Oh, yeah.
Sorry. Yeah.
For the individual guys, I don't have a good sense of the halo mass, but you know I use Peter Baruzzi's empirical relation that I derive from the universe machine and make some observational cuts. So I don't think I have a great answer for the halo masses of individual things, but I don't think this is inconsistent, but I haven't checked.
Okay.
Yeah.
Thank you very much again to Jake while we are introducing